Hello everyone, and welcome back to another short topic video. This one is on potential energy diagrams. So you can see I have a diagram right here, a very simple diagram, not overly complex. Energy increasing up the y-axis. X-axis is labeled the pathway, the reaction pathway from reactants to products. I did give a couple of points here, 10, 50, and 150 kilojoules. If you had to draw a particular diagram like this, you could label it numbered however you like, depending on what's required for your question. All right. So let's have a look at this diagram. You're going to be asked a couple of different things in terms of either interpreting a diagram or possibly drawing this particular type of diagram. So you may be asked energy of reactants, energy of products. That's two very common questions. So my reactants right there, let's say 50 kilojoules, products over there, and we'll say 10 kilojoules for the products. One of the things you might have to label would be the activation energy. So as your reactants are colliding, they're building up energy. They want to react and turn into products. They can only do that when they overcome this activation energy. How much energy is required to turn our reactants into products? So on your graph, if you kind of see where I'm going to draw this, I'm going to draw a line across right here. So from where the reactants begin to the top of the hill is known as the activation energy. How much energy do they need to build up to sort of get over that hill and turn into products? In this particular graph that I drew, let's say the activation energy is 100, right? So the reactants start at 50, the top of the hill is 150. The difference between the two, this would be, let's say, 100 kilojoules. And you could also label your arrow right there, EA, activation energy or energy of activation. Something else you might have to label is the delta H. The delta H is the difference of where the reactants begin and the products finish. So if I'm labeling this in terms of their energy, I'm going to draw another line across the bottom here. And the difference between reactants and products is the delta H. So here's my delta H, and of course, final minus initial. So final energy minus initial, 10 minus 50, and that gives me a delta H of negative 40 kilojoules. Because delta H is negative, I now know that this graph is showing me an exothermic reaction. All right, so that's something that you might have to show on this. You may also be asked to show the location of the transition state or the activated complex. These are sort of in-between molecules that are created as the reactants are colliding. They're not reactants, they're not products. It's something totally different and really unimportant to us in terms of what they are, but their location is important. Where do the activated complex or the transition state, where does it actually occur? And it occurs sort of right there at the top of the hill. If there's enough energy built up, if you can overcome this activation energy, then our transition state breaks apart and it turns into the products. You can label this TS, sometimes I use transition state, or sometimes I will label it AC, activated complex. If you use either one of those on your diagrams, I'll know what you're referring to, so either one of them is fine. The last thing you might want to show is what if this reaction had a catalyst introduced? Okay, so knowing what a catalyst does, it lowers the activation energy for a particular reaction and therefore increasing the speed, the rate of the reaction. So a catalyst is often showed like this with a second dotted line here showing a lower sort of hill, a lower peak to get over, a lower activation energy. All right, and that's the reason that the reaction speeds up. It doesn't need, as long time-wise to build up the energy required to reach your product states. Okay, so lowering the activation energy increases your rate of reaction, and doing a catalyst or adding a catalyst will do that. So that's just one sort of graph that you're going to need to know. That would be an exothermic graph. Let's go ahead and I'll just slide this down here to the next example. So again, I've got my reactants, products, I've got energy on the y-axis, pathway on the x-axis, and I'm going to show the location of my activation energy. So just kind of drawing a line across here like this. So from where my reactants begin to the top of the hill is your activation energy. And in this example, we would say the activation energy is, let's say, 100 kilojoules, right? So 150 at the top of the hill, reactants are starting at 50, so the difference between the two, 100 kilojoules. Delta H is still the difference of reactants and products, so where the products finish and where the reactants begin, the difference in their energy, so it's right here. And in this example, your delta H is the products here, let's say this is about 100 and 50, so the final 100 minus initial 50 gives me a positive 50 kilojoules for this one. Because I know delta H is positive, I can now say that this is an endothermic reaction. You might also be asked to show your transition state or your activated complex. Of course, same place at the top of the hill. All right, always in the same place in these graphs. And then finally, what would a catalyst look like if I added a catalyst to this reaction? So again, kind of a second dotted line here, a lower peak to get over, a lower activation energy for your catalyst, which is why the reaction speeds up. I don't need to take as long, it doesn't require as much time to reach the top of the hill in order for my transition state to turn into products. This is why the catalyst speeds up the reaction, right? It doesn't need as long time-wise to create that much energy. So these are just some things that you might be asked to show if you're asked to graph a particular reaction like this, or maybe you're going to be given a graph like this and asked to interpret what is the value of delta H, what is the value of the activation energy, is this particular reaction endo or exothermic, all right? So these are just some things you can have a look at. There are questions in your workbook that you can try similar to this. I do believe they're looking at a graph and interpreting, but you could also do the reverse and try to make your own, label your own endograph and your own exothermic graph, and see if you can label all the pieces and give a value to your activation energy and your delta H. As always, if you have any questions, please reach out and let me know. We will be covering this in class, and some of us already have if you're watching this video. Good luck interpreting these graphs, and don't forget to do the questions in your workbook. As always, thanks for watching and have a good day.